Hello everyone, welcome to lecture 39 of this NPTEL course on Riemannian geometry. In the previous lecture I proved the Gauss lemma. So let me remind you of what the statement was. So the notation was as follows. So a geodesic ball of centered at P of radius epsilon is basically the image under the exponential map of this ball of radius epsilon at 0 in the tangent space at P, such that the exponential map is a diffeomorphism in a neighbourhood of the closure of this ball in the tangent space, right. So the picture is as follows. So you have your M, you have your origin here, you take this ball of radius epsilon, this is P, and you project that down by the exponential map to some neighbourhood of P, and this epsilon is chosen so that the closure of this ball is contained in a neighbourhood in which the exponential map is a diffeomorphism, right. Then for any eta less than equal to epsilon, we denote by the image under the exponential map of this sphere in the tangent space, we denote that by partial of up eta, and the point of this notation is that this del up eta turns out to be the topological boundary of up eta, right. So then the Gauss lemma basically says that if you look at this radial vector field, since this lies inside a region on which the exponential map is a diffeomorphism, I can use normal coordinates there. With respect to the normal coordinates, I have this radial vector field del by del rp. The Gauss lemma says that this radial vector field is actually orthogonal to these boundary spheres. So in other words, if you take a vector here that corresponds to a geodesic here, the radial vector field will be given by this, and the claim is that this is orthogonal to all vectors of this form, right. So this is orthogonal to all vectors of this form. Alright, and then as a consequence of that, we derived the following nice relationship, that the gradient of this radial distance function, recall that the radial distance function was precisely the square root, the usual distance function in terms of these normal coordinates, right. So the gradient of that turns out to be precisely this radial vector field. So the point of this lecture is to try to understand the local behavior of geodesics by exploiting the Gauss lemma, okay. So recall that we already, as a consequence of the first variation formula, we proved that if you have a critical point of the length functional, in particular if there is a curve that minimizes sort of attains the minimum for the length of all curves between 2 points, then that ought to be a smooth geodesic, right. But the converse we saw for these great circles etc., the converse is not true. So today we would like to prove a sort of local version of the converse, that at least locally all geodesics are minimizing. So before that, let me define what I mean by minimizing geodesic. So here is a definition. We say that a curve gamma in P to Q is minimal. So you are going to hear a lot of this word for the rest of the course. So we say that this curve is minimal if for all other sigma the length of sigma is at least as much as the length of gamma, okay. So so let me make a couple of remarks. Firstly, as I was saying, by the first variation formula implies that if gamma is minimal, then gamma is a geodesic, right. Okay, so that was the consequence of the first variation formula. The second point is that suppose gamma is a curve from A to B to M, then for any times T1 and T2, the restriction of gamma is also going to be minimal. Okay, so the point is that let us say you have your P and Q here and you have your gamma between them. Now suppose you choose sometimes sorry, this is P and Q, right. So let us say you pick two time intervals, sorry, let me draw this again. Okay, so let us say we have two time intervals and corresponding to these 2 points gamma of T1 and gamma of T2. Suppose there is another curve sigma between gamma of T1 and gamma of T2 which is shorter than this segment of gamma between gamma of T1 and gamma of T2, then of course even to go from P to Q you could have taken a shortcut via sigma, right. So, so then that would contradict the fact that gamma is minimal. So the point is that if you are given a minimal curve, then on any smaller subinterval gamma continues to be minimal. Okay. So more generally one can then define given any interval I, gamma is called minimal if for all T1 T2 in this interval, T1 less than T2, gamma restricted to the compact interval T1 T2 is minimal. Okay. So the main goal for this lecture is to prove the following theorem. For any point P in M, there exists a neighbourhood W of P and an epsilon positive such that the following holds, that for all x and y in W there exists a unique geodesic gamma from let us say 0 1 to M such that gamma of 0 is x, gamma of 1 is y. Gamma is a short geodesic in the sense that the length is smaller than epsilon, and crucially gamma is minimal. Okay. So let me just draw a picture. So this is our M, let us say this is our point P, then I am claiming that there exists some neighbourhood W, so that if you take any two points in W, there will be a unique minimal geodesic connecting these two, and as in the picture you can see that the minimal geodesic is allowed to leave W. So let me make that as a remark. We do not say that that is gamma is allowed to leave W. Okay. In fact, with some more effort one can indeed choose W to be what is called convex, i.e. gamma will stay inside W, but for our purpose this is not needed. Okay, so we will take the easy way out and prove a slightly weaker result. Okay, in any case, throughout the proof you should sort of keep this picture in mind, that given any x and y you can join them by a short geodesic whose length is less than epsilon. Okay. All right. So before I give you the proof, let me give you a quick corollary. So let gamma be a geodesic okay. Then for any T naught in the interval there exists a delta, of course depending on T naught, such that if you take the restriction of gamma to this interval, small interval around T naught, this is minimal. Okay. So that means the upshot is exactly what I had claimed a few lectures back, that even though a geodesic may not be globally a minimal curve, geodesic implies locally minimizing at least. Okay. All right. So how do you prove this? It's not difficult at all. So we just let P be this point. So this is our geodesic. We let P be the point gamma of T naught. Now by the theorem there exists this neighbourhood W such that any two points can be are basically joined by a unique geodesic. Unique is important. So right, so choose delta small enough such that this entire segment, let us say this is gamma of T naught minus delta, this is gamma of T naught plus delta, this entire segment is contained inside W. So gamma of T naught minus delta to T naught plus delta is completely contained inside W. Okay, so then for any T1 and T2 in this interval, by sorry, I need another condition, that also choose delta small enough such that the length of that segment is smaller than epsilon. Where this epsilon is the same epsilon that is given by the theorem. Okay, so then given any T1 and T2 in this interval, okay, by the theorem there exists a unique geodesic from gamma of T1 to gamma of T2 with length less than epsilon, which is also minimal, okay. But then we already have a geodesic connecting gamma of T1 and gamma of T2, right, namely gamma itself. So that has to be the geodesic that the theorem is referring to. Okay. So by the uniqueness part of the theorem, gamma has to be the minimal geodesic. From the theorem, and hence we are done. Okay. So let me maybe go back to the statement of the theorem. So so maybe I should say, moreover, I should change the wording a little bit. Moreover, gamma is minimal. So the theorem asserts that you have a unique geodesic of length smaller than epsilon connecting x and y. That is the first part of the theorem, and then it turns out that this unique geodesic is actually a minimal geodesic. Okay. So that is how you should read the theorem. Alright. So now let's prove the theorem. Okay, so before I prove the complete theorem, I need the following lemma. Okay, so so let U P epsilon be a geodesic ball okay of radius epsilon centered at P. Now suppose sigma is an admissible curve in the complement of P in this geodesic ball, then one has the following estimate on the length of sigma. So the length of sigma will be at least as much as the difference between the radial distances from between the two endpoints of sigma. Okay. With equality, if and only if for some reparametrization so again, because we are dealing with length, there is always this sort of annoying fact that one has to maybe constantly keep reparametrizing. So for some reparametrization phi, if you look at sigma composed with phi, then that is given by a radial geodesic by exponential of T V for some V in the tangent space. Okay. So so let me just draw maybe a picture explaining. So so in particular, what this implies is that radial geodesics are minimal. Okay, so this already proves a little. I mean, this is sort of a weaker version of what we are anyway claiming in the theorem, right? So let me maybe draw a picture illustrating what is really happening. So again, let us say you have your tangent space and you have your surface here. Okay, and this is your sort of geodesic ball and corresponding to some neighbourhood U P epsilon here. So what this says is that suppose you let us look at two shells. Okay. So maybe I'll draw the inner shell with a sort of green color. Oh, sorry. And the outer shell with a pink color. So here you correspondingly have these. Now suppose you have a curve sigma which is between these two right. So suppose you have a curve sigma that goes between these two shells, then what this statement is claiming is that if you instead take the radial line, right, that will be the shortest path between these two shells. Okay. So in particular the radial geodesics are minimal geodesics. Okay. So how do you prove this lemma? So let us just start by reparametrizing. So by reparametrizing, suppose without loss of generality that that the speed of sigma is identically 1. You can always do that, right, you can always take an arc length parametrization. So now let rho of t be the following function, let this be r composed with sigma of t, or rp composed with sigma of t, where rp is the radial distance as usual. Okay. So then what is the derivative of rho? Well, that is just the gradient of rp inner product with sigma dot, right. So in fact maybe let me write down the intermediate step. So by the chain rule the derivative of this is simply this, but then by the definition of gradient this is simply the inner product of this. Okay. All of this is happening at sigma of t. So then by the Cauchy-Schwarz inequality, if you take the norm of rho prime of t, then that is going to be less than equal to the individual norms of these vector fields. But now we saw previously that that this guy is just the norm of del by del rp, and we have also seen that the norm of del by del rp is 1, right. Similarly by our reparametrization this is 1, so the product is just going to be 1. Okay. Or rather let me yeah, so the product I mean this is going to be less than this is going to be equal to sigma dot norm sigma dot of t, okay, which is of course 1, but let us just keep it as norm sigma dot of t for now. So now if you integrate the two sides, note that the length of sigma is precisely the integral of the speed, okay, but then what this says is that this is bigger than the integral of absolute value of rho prime of t, but then by the triangle inequality you can take the absolute value outside, or rather the triangle inequality applied to Riemann sums. This is bigger than or equal to the absolute value of this, but then this integral by the fundamental theorem of calculus is just rho of 1 minus rho of 0, okay. So this is exactly what we had claimed, okay. This is exactly what the lemma claims. Also, when do you have equality? So equality is when these are proportional to each other. So the equality in Cauchy-Schwarz, if you remember, happens if the two vectors are proportional to each other. So equality if and only if sigma dot of t is lambda del by del rp, So then by firstly if at all maybe reversing the orientation, one can assume that lambda is positive. Also because the speed is 1, lambda will be 1. So lambda is plus minus 1 because the speed is 1. Also by possibly reversing orientation, which does not change the length at all, we can assume that that lambda is actually 1. Okay. So this implies that sigma dot of t is del by del rp at sigma t for all t, but then that means that sigma has to be a radial path. So this implies that sigma of t is actually the exponential of for some v. In fact, v is just the initial velocity vector of sigma, right. So this proves the lemma. So now I am going to use this to prove our main theorem. Okay. So there are two parts to the main theorem. So there are the first step is to show some sort of weak convexity. Okay, so in the first part I will actually show that there exists a unique geodesic connecting these two, and in the second step I will show that that unique geodesic happens to also be minimal. Okay. So for this I am going to use the fact that the exponential map is a diffeomorphism. So recall that we had this map phi from the domain of the exponential map to M, where a vector xi basically goes to pi of xi comma exponential of xi. Okay. So this is a local diffeomorphism near any point in the domain of the exponential map of this type, right. So choose a neighbourhood u of p and an epsilon positive such that if you look at this set v tilde, this is the set of all tangent vectors of the form x comma v, where x belongs to u and the norm of v is less than epsilon. So such that if v tilde is this, then f is a diffeo on v tilde. Okay, so one can always choose such a neighbourhood v tilde. Okay, so now my w, which the theorem claims that there exists this w, my w is going to be the following set. So let w be the open subset of M containing P such that the product w cross w is contained in the image of v tilde. So remember, the image of v tilde under this phi is a subset of M cross M, and just by the fact that product sort of domains form a basis for the product topology on M cross M, we can always find a w such that w cross w is contained in M cross M, because p comma p is a point, because p comma p is a point here. Okay, so one can always find such a product domain contained completely inside phi of v tilde. So now suppose x and y are 2 points in W. Okay, then by definition, because they are contained in this set, there exists a vector v in the tangent space to M at x such that y is given by exponential of v at x. Okay, and v is less than, the norm of v is less than epsilon. Okay. So in other words, all I am saying is that y is phi of this vector x comma v. Okay. Right, now just let this gamma be equal to exponential of TV. So then clearly gamma of 0 is x, it is a geodesic obviously, gamma of 1 is y, and the length of gamma is basically I mean it is basically equal to the norm of V, which is less than epsilon by our choice. Okay. So we have found a geodesic as claimed in the theorem. Why is this unique? So I want to claim that this is unique. So claim that if gamma tilde from let us say 0 1 to m is another geodesic such that gamma tilde of 0 is x and gamma tilde of 1 is y, and the length of gamma tilde is less than epsilon, then in fact I want to claim that gamma tilde is identically equal to gamma. Okay, what is the proof of this? Well, if so, then let V tilde be gamma tilde prime at 0, be the initial velocity vector of V tilde. Then clearly because the length is shorter than epsilon, clearly the norm of V tilde has to be also less than epsilon, right, because what is the length? It is the integral of the speed is constant equal to the norm of V tilde because it is a geodesic, right. But then note that W is contained in U, so X is also in U, and which would mean that X tilde V tilde is in V tilde and Y is also equal to this, right, because we are assuming that this is another such geodesic, but we already know that this is equal to this. So that contradicts the injectivity of phi, but phi is a diffeo restricted to V tilde, so this is a contradiction because a diffeomorphism in particular has to be also an injective map. So this is a contradiction. Okay, so that means now we have found a geodesic connecting x and y of length less than epsilon, and that will be the unique such geodesic. Now I want to claim that so to finish the proof, the second step is that gamma is minimal. Okay. So let u x epsilon be this geodesic ball given by the exponential of the exponential at x of this ball of radius epsilon. Okay. So note that the exponential map at x by our choice, the choices we have made of epsilon and V tilde is a diffeo. Okay. So then our claim is that W is contained inside this. Okay. What is the proof? Well, let Z be a point in W, then that means by our choice of W that this pair x comma W is in the image of V tilde under phi, right, which means that there exists a vector, let us say W, a vector V prime in the tangent space at x with norm of V prime less than epsilon such that Z is given by the exponential at x of v prime. But then I mean by definition of this set, this means that z belongs to this, okay. Alright, so now suppose, how do you show minimality? So now let sigma be a path in M connecting x and y, okay. So suppose sigma is completely contained inside this, then by our previous lemma, the length of sigma will be bigger than the length of the radial geodesic connecting x to p, which is of course gamma, right. So gamma in this case is the radial geodesic connecting x and y. So length of sigma will have to be bigger than or equal to gamma. On the other hand, if sigma leaves this set at some point t naught, then by the same lemma the so the setting is that you have your x, you have this, at some point let us say your sigma leaves here and then maybe comes back to join up with y, but then if you look at the stretch of the curve from here to here, that is already the length will be larger than the length of the radial geodesic from x to the point wherever it leaves your geodesic sphere, okay. So then I mean already this length is epsilon because you are looking at a geodesic sphere of size epsilon. So then already the length of sigma restricted to this interval 0 to t naught is already epsilon, is bigger than epsilon, right, which is bigger than the length of gamma. So in either case we have seen that the length of sigma is bigger than or equal to the length of gamma. So gamma has to be a minimal geodesic, okay. So that completes the proof of the theorem. Alright, so we have now shown that even though the geodesics may not be globally minimizing, they are at least locally minimizing. So for the next few lectures I will explore this more sort of global minimization problem for geodesics. So first I will in the next couple of lectures I will talk about, I will define a metric space structure on a Riemannian manifold, and then we will talk about some completeness properties of this metric space, and then after that we will move on to studying whether if you are given a geodesic, when can you say it is minimizing or not, right. Alright, so that is it for this lecture. Thank you for your attention and I will see you next time. Thank you.